talks concerns that some properties which is known about the anti-canonical divisors of smooth del Pezzo surface extends to the general polarization of del Pezzo surfaces. And I'll use notation ST is a smooth del Pezzo surface of degree D. D is K square. And I consider three things. First one is K stability. This is related to existence of some metrics and constant scalar curvature, Kähler metric, and Kähler-Einstein metrics. And second one is A polar cylindricity. Which is one kind of compactification, which is a boundary is a polar divisor. And third one is flexibility. Stability of a fine corner of the surface. SD. This is related to some automorphism groups of affine variety. And what is ample divisor on the del Pezzo surface? It is very easily characterized because A is ample if and only if by Kohn theorem A and every line is positive for every -1 curve. And let me introduce the pseudo-effective threshold, which is defined by supremum of lambda such that KSD KX plus lambda A is pseudo-effective. A is ample divisor for a given polarization. And then this invariant is called Nakayama constant. Or the reciprocal is called the Fujita number. Among the people who studied the Manning conjecture on the del Pezzo surfaces. And then let's think about the divisor Kx plus KSD plus UA. This divisor lies on the boundary of the Morricone. So this divisor is generated by -1 curve or -0 curves. So let delta SA to be a smallest face of Morricone such that it containing this divisor. And then if you contract, let pi to be a contraction of this face, then this is a birational or conic bundle. So we can see that the Ks plus mu A is sum of -1 curves or 9 minus t, a minus t. sum of -1 curves plus some fibers, B, fiber of conic bundles. So we can write, and for any ample divisors on the Pezzo surface, which is can be written in 1 over mu minus ks plus these divisors, or so by ampleness condition, this coefficient is ranges in 0 and bounded by 1. But A is, and A is positive. Yes. Okay. Now let me consider the first condition, K stability. Actually, K stability is some positivity of a Donaldson-Futak invariant among the polarized families, a certain polarized family called the test configuration. Actually, we say a polarized family, polarization X and L is stable when the Donaldson-Futak invariant is positive for all test configuration. But by theorem of Joonyeong, Shu, and Chiri, we only check in the special test configuration. I'll omit the details. And the central theorem in Kähler geometry is to find the constant scalar curvature Kähler matrix. The important conjecture of Yau, Tian, Donaldson conjecture says that the existence of constant scalar curvature Kähler matrix in C1L is equivalent to the notion of K stability. Actually, exactly speaking, K polystable. And now it is a theorem for the case L is anti-canonical divisor by Shuhyung Chen and Sun and Donaldson and Tian independently. And for a general polarization by Donaldson and Stoppa proved that if exists constant scalar curvature Kähler metric in C1L, then it is K stable when the automorphism group is discrete. And first sufficient condition to have K stable is by Tian's alpha invariant. Alpha invariant. It says by Dmai Kola and Tian, then X is Fan orbital if the alpha invariant is alpha invariant of X and minus K is greater than n over n plus 1, then X is Kähler-Einstein. And then the Sano and the Odaka directly proved if the alpha invariant of anti-canonical polarization is greater than n over n plus 1, then X is K-stable. They used some in pure algebraic method. They proved this one directly. I forgot the definition of alpha invariant. Alpha invariant is defined by for a polarization X and L, then the supremum of lambda such that X and lambda D is log canonical for any Q effective divisor D, which is numerically L. And then Durban generalized the result of Sano and Odaka. Durban's theorem says if X is a Q-Gorenstein log canonical variety, and then let nu is a slope of this Ln plus minus 1. It's a numerical value. It depends on Xn between polarization. Yeah?
Bigger. Coming to small.
What?
크게 적으라고.
Sorry. And then if first alpha invariant of X and L is bigger than n over n plus 1 times nu X and L. And second, Leibniz condition, Kx minus n over n plus 1 nu L times L is left. Then the polarization is K-stable. Yeah. Okay. When we think about in the del Pezzo surface cases, this property is very easy to check because we only compute in the intersection of lines. So the hardest part is to compute this alpha invariant. So I'll introduce first known example in the anti-canonical divisor case. That is a minus k case. Charles proved the alpha invariant of K, SD case is the alpha is 1 or 5 over 6 when the D is one case, and these two cases 5 over 6 or 3 over 4. These three case 3 over 4 or 2, 3. This one is a general case. This is a codimension 1 cases. So let's prove this degree 1 cases. It is very simple. Degree 1 case. Now suppose X and D is not log canonical. Well, D is numerically minus K. Then, not log canonical at the point P. Then we can find anti-canonical divisor passing through the point P, let it be d prime in the minus k, which is passing through the point P. And by convexity of low canonicity, we can assume D does not contain D prime. So D prime intersection D is k squared is 1. And then it is greater than or equal to multiplicity of point P and D prime and multiplicity of D. But by definition of low canonicity, non-low canonicity, it is greater than 1. So it is contradiction. It's very easy. Actually, the hard part is cubic cases. Okay, now I generalized this to Del Pezzo 1 degree 1 general polarization cases. So I wanted to, I tried to compute all alpha invariant for any ample divisors, but it turns out that it is very hard to compute all exact value of alpha invariant. So I decided to compute, classify, it satisfies these conditions. So, but first I computed some other invariant, alpha C, X and L, which is defined as supremum of lambda such that the pair is log canonical along a curve. And D is numerically minus numerical L, which is just a reciprocal of a maximal multiplicity along a curve. And then we can prove the lemma. And C, if C is less than 2 over 3, then the low canonical center of X and CD, D is numerical minus numerical L, cannot be point. So the alpha invariant is we have alpha invariant is always greater than or equal to 2 over 3, while alpha is alpha C. So I computed this. Actually, I computed this alpha C. When the case of tiger is a curve case. For example, this pi is birational cases. Then A is it can be written A kx plus sum of AI, EI, and then we can put all the A1 is greater than A2, dot dot dot, and so on. So and then this is a degree 1 case, so AA, and then omega to be a sum of from I is 2 and to 8 of AIs. In the case of omega is less than or equal to 1, then alpha invariant of X and L is greater than or equal to 2 over 3, greater than 2 over 3, or 2 over 1 plus 2A1 plus omega. Yes. And then by classification of all these alpha invariant, it turns out this Nephenis condition is strict. So my theorem is S1 is what is my theorem? If minus k S1 minus n plus 1 2/3 do x and L is left, then S1 and L is KAIST. This is the theorem. The second condition is more strict than the first one, alpha invariant condition. And moreover, this one is very easy to check. Actually, moreover, if minus k, this divisor intersection with 6h minus 3e1 minus e2. Then is KAIST. You only need computation of the intersection with this minus 1 curve.
So under the second condition,
Yeah.
then can you prove the one, or you don't need the one to prove K-stable?
Yeah.
So what do you mean?
Just by calculation of alpha invariant.
So
I proved that it satisfies this one, then automatically the first one is satisfied. Yes. And for example, minus k plus 1/10 sum of EI. For this divisor is K-stable. Now I look at the cylindericity. The A polar cylinder is a subset, affine subset U in X. Is isomorphic to this is defined by X minus support of A polar divisor D. D is numerically A, and then which look like a cylinder-like set C1. The boundary is support of A polar divisor. And this is related to some existence of affine cone, existence of additive action on the affine cone. That X had to be a affine cone. X and N. And then Kishimoto, Prokhorov, and Zeidenberg theorem says that if X possesses a polar cylinder, if and only if X hat has a regular effective additive group action, GA action. This is useful theorem. And GA action is also related to singularity theory. The theorem of Flanner and Zeidenberg says that Briscoe palm hypersurface singularity. Briscoe palm singularity is a cyclic quotient singularity. If and only if it has a additive group action. Briscoe palm singularity is just defined by xp plus yq plus c r is 0. So to generalize to higher dimensional cases, they questioned about the existence of additive group action. They questioned x cube plus y cube z cube 0 in C4 has GA action. Actually, it has a rational singularity. So they proposed a question on the three-dimensional cases. It has a GA action, but the answer is no. Answer is no. By Chelsov, and actually we proved the non-existence of minus k polar cylinder in cubic hypersurface in P3. Get together all work of Kishimoto and Prokhorov and Zeidenberg, and our work says the k polar cylinder, minus k polar cylinder doesn't exist in the case of degree 1 and 2 and 3, and does exist, minus k polar cylinder exists in the degree greater than or equal to 4 cases. And actually Prokhorov and Zeidenberg proved there is always exist polar S is if S is a rational surface, then always exists some polarization of S has L polar cylinder. Although the cubic surface does not have a k polar cylinder, but by theorem this there exists some ample divisor which has a L polar cylinder. So Prokhorov questioned that can we classify the ample divisors which has L polar cylinders in the cubic surfaces. So, but the answer is very simple. It's very simple. If T is greater than 3, then A polar cylinder exists if and only if D is only except for D is 3 and A is minus K. This is theorem. Theorem of same as Chelsov and Bach. Now, by using this description, I can prove the bidirectional cases that there is a A polar cylinder. Let us think about the cubic cases. And then we can write A to be a 1 over mu minus K plus sum of 1 to 6 AI EI. And then we assumed A is not minus K. So sum of coefficient, one of coefficient is positive. And then we can contract this exceptional divisor to the Pn, P2. Then there will be a point pi E1 and the other 5 points here. And then take a unique conic passing through this other 5 points. Let it be a C. And then take a tangent line to the C, and which is passing through the pi E1. Let it called L. And then P2 minus C and L is a cylinder, because A1 star cross A1. This is isomorphic. Because actually the fiber of this cylinder is just a conic passing through the conic tangent to the line with multiplicity 4. These conics is fibers on this cylinder. And then take a divisor minus K is 1 minus 2 epsilon L plus 1 plus epsilon C. This is numerically minus K. And then you think in cubic surface, which is 1 minus 2 epsilon L bar plus epsilon C bar plus epsilon EI 6 plus minus 2 epsilon E1. But this is not effective divisor. This is minus. But we can add this residual exceptional divisors. So A is equivalent to this minus K plus sum of AI EI. By summing up, these coefficient becomes A1 minus 2 epsilon. So we can take epsilon very small, then the A is effective divisor. And then the S3 minus A is isomorphic to P2 minus C and L, which is a cylinder. Because this divisor has all exceptional divisors, so this set is isomorphic to this set. And then, yes, higher degree case is very simple, but if we dive into the degree 2 or 1 cases, the problem becomes super hard. So we have some partial answers on the degree 2 cases. If degree 2 cases, we have if kx is A is 1 over mu minus k plus AE plus just one exceptional divisors, then then S2 and A does not have apolar cylinder. But higher rank case, if there is some other exceptional curvature, we don't have some partial answers, but not complete. And now I talk about the flexibility of affine cone of the Pezzo surfaces. Before that, let me define a group element G in Z, X, M transitively. It means for any pairwise distinct point, there is a G such that any pair, for any pair is transitive. So, and the special automorphism group in automorphism group is generated by all algebraic one parameter unipotent subgroup, which is a special automorphism group. And when we call X is flexible, if any smooth point, for any smooth point, that the tangent space is spanned by just a tangent vector to the orbit, Hx. H is a one parameter unipotent subgroup of automorphism groups. This is definition. And Arzan's chap, Flanner, Kaliman, Kushebau, and Zeidenberg proved that the following is equivalent. And if X is a dimension of X is greater than 2, then X is affine algebraic variety. Then the first one, X is flexible, and the special automorphism group X transitively. In smooth locus of X. And third one, samely, special automorphism group X infinitely transitive. Infinity transitive means M transitive with M for all M. So this theorem says that the following is equivalent. And also they proved any flexible variety is unidirectional. So Bogomolov, Karamazov, Krazemanov, and Kuyumjian conjecture that every unidirectional variety is stably bidirectional to flexible variety. They conjectured this conjecture, and then they proved in some cases, for example, any cubic hypersurface is stably bidirectional to flexible variety, and some quartic threefold with single locus along a line has this property, and Pano threefold with of degree 8 cases they solved this conjecture. And then Kaliman and Zeidenberg proved every hypersurface in A n plus 2 look like UV is F. It's a homogeneous polynomial, and this hypersurface is flexible. So flexible. This look like a suspension of this equation. And then they also proved a fine cone over toric variety also flexible. So we explored into the Del Pezzo surface, a fine cone over Del Pezzo surfaces degree greater than 5 cases are toric, so the fine cone is flexible. So we can think about the degree 5 or 4 cases. Actually, Perepechiko proved a fine cone over S5 is flexible for any polarization. And for the S4 cases, they proved in the S4 and minus K, and some other ample divisor, some case. Actually, there is a criterion to be flexible in terms of cylinder structure. The criterion is to introduce the criterion. I'll introduce some definitions. The set W is invariant to a cylinder plus A1. Then if W intersection U is pi inverse where pi is a first projection of cylinder, it means if the point is in the cylinder, then W contains whole fiber. And transversal covering mean by this union of cylinders. This is a cylinder, and it satisfies. There's no proper offset. W, which is invariant or cylinder UI. And then we have a criterion. If X has a transversal covering by H polar cylinder, A polar cylinder, then the affine cone is flexible. So if we produce many cylinders, it covers the variety, and then we have a affine cone is flexible. But the invariant condition is I think it is very automatic if we produce so many cylinders. And I sketch a proof of a Peripetchikos region. It's very easy. Let me think about degree 4 case and anti-canonical polarization. And then it has 5 disjoint exceptional curves. And for each exceptional curve, there is a -1 curve, 5 -1 curves, which intersects EI. And then contract this 5 cylinder, 5 -1 curves into the P2. Then we have 5 points. And take a conic. Actually, this conic is image of this EI. Then take a arbitrary tangent line, and then there are infinitely many family of cylinders. And then, but it does not cover exceptional curves. These exceptional curves, these 5 exceptional curves, and this conic. So this family of cylinder does not accept only these 6 curves. It covers it except only these 6 curves. But we can do the same thing for other exceptional divisors. So it covers all S4, and we need to show that the non-existence of invariant subset, but this is very easy. And then actually he used a cylinder like this one, so it doesn't cover all ample divisors, but with Park for any polarization so affine cone for A is flexible. It's short. We produced many cylinders, so for every ample divisors cases, but we can think about cubic cases. In these cases, except only anti-canonical divisor, there is exists always a cylinder, but so far we have only one cylinder, so we don't know the answers on the cubic cases so far. Yeah. I stop here.
So, any questions?